Welcome to Physics for Architects. Please watch this video and answer the online questions before the first day of class. This course mainly covers the branch of physics called mechanics, and it's intended mainly to leave you in excellent shape to take someday an architectural structures course if you are in the architecture program. Or if you're not in the architecture program, if you learned mechanics before in high school, or even if you didn't, you'll come away with, I think, a firmer grasp of Newton's laws of motion and how to apply them and how they connect to what keeps architectural structures standing up. So Physics 8 covers a pretty similar set of topics to other introductory college physics courses like Physics 101, which is mainly for pre-meds, or Physics 150, which is mainly for engineers, or Physics 170, which is mainly for physics majors. So what makes it physics for architects? So one thing is that typically about half of the students in this course are architecture majors. So you're in the undergraduate architecture program at UPenn, or a closely related program like the fine arts program or the design program. Having your own course lets us tailor the course to your interests and to your background. So I have sat in on many of your studio critiques over the years, so I've got at least a little bit of idea what you do in the courses that take up the bulk of your time. I also certainly know how much time you put into those courses. I've tried to learn over the years how to make the course connect with you and how to make it compatible with what you do. For example, we don't meet on Tuesday and Thursday afternoons, even though that would be a convenient choice because I know that those of you in the architecture program are in studio Tuesday and Thursday afternoons. So once we've covered the basics of Newton's laws of mechanics, we'll spend several weeks applying what we've learned to study topics related to architectural structures. So we'll learn how to analyze trusses, which are those kind of triangular shaped things you might have seen on railroad bridges. You know, anytime you see things kind of broken up into triangles, that's typically a version of a truss. We'll study topics related to architectural structures like trusses, cables, beams, and so on. I think this is a fun way to connect the physics with applications, and they're applications that you'll see again if someday you take a structures course. So I know that you're accustomed to working together, and I know that's true of the students in the undergrad architecture program, and then we also often get a lot of students from the Huntsman program. I know that you're really accustomed to working together on case studies in that program. So we will do most of the learning in this course cooperatively in small groups. I think it will be fun to be able to spend the time really learning together. For a long time, architects have been designing structures to span spaces. You might ask, is physics relevant to this pursuit of spanning spaces with structures? I think it is. So let's make a model of a bridge, which is just a plank being held up on two ends. This is actually also going to introduce us to this concept of models. Physics often uses models to take a real world problem and to turn it into a form that is amenable to pencil and paper analysis. A wooden plank. And that wooden plank is going to be supported by two scales. And then we're going to move one of the scales closer to the center, and we'll ask, how does what the two scales read change? Just to show you, it's basically an 8-kilogram plank. I'll put the plank on a single scale. What does each scale read? For now, we'll just see what the result is, and then on the first day of class, you will work through this same demonstration, and you'll try to figure out within your group of 3 people what the rule is that governs how the weight is divided between the two scales. We'll think this through more systematically a couple of weeks from now. So let's see what happens. And it looks as if instead of one scale reading 8 kilograms or just under 8 kilograms, instead we have 2 scales, each one reading just under 4 kilograms. I'm just showing you the answer. You're going to talk it through with your classmates on the first day of class. Now let's see what happens if we move this scale over to the 3/4 mark. And you can just make a note. It seems like this one now reads a larger value. This one now reads a smaller value. You could also just make a mental note of what the two numbers add up to. You could make a mental note of the ratio of the two numbers. You could note how far this scale is from the middle, and you could note how far this scale is from the middle. So again, we said physics often use models. We're going to use 2 different models to demonstrate the physics behind the 1981 Hyatt Regency walkway collapse in Kansas City. This is a 4th floor walkway. This is a 2nd floor walkway. Each floor of this walkway is connected to the ceiling by some really long metal rods that basically go from ceiling down to the lowest level. It's a little bit analogous to a person hanging onto a rope suspended from the ceiling. The folks on the construction site decided that it was an incredible nuisance to try to connect to the same threaded rod going all the way up to the ceiling. So instead, what they did on the construction site is they connected the top floor to the ceiling, and then they connected the bottom floor to the top floor. So then we'll erase this original connection that the architect drew. So the architect said you should have a threaded rod going all the way from the ceiling down to the floor, and then each of these suspended walkway levels should connect to that same threaded rod. And what was actually done on the construction site, this was a relatively short cable going from the ceiling down to the top floor, and then there's a cable from the top floor down to the next floor below it. My analog for this is, imagine this top floor hanging onto a rope, and then there's a friend. The lower floor wants to hang from the ceiling also. One option is I grab the rope over here, and then my friend grabs the same rope down below me. In that case, I think I'm carrying my weight, my friend is carrying her weight. The other option is I'll grab onto the rope up here, and then my friend, instead of grabbing onto the same rope, she grabs onto my feet. So you can imagine what happens where I'm trying to grab onto the rope, because my hands have to hold not only my weight, but her weight as well. On this side, the walkway structure as designed by the architect. Imagine that this is actually some big girder on the ceiling, and then here's the upper level of the skywalk and a middle level and a lower level. One long threaded rod here, and there's one long threaded rod here. This bridge deck is represented by a piece of PVC tubing. It holds itself to each threaded rod with this clothespin. So this clothespin represents a nut to attach this deck to its threaded rods. The threaded rod is represented by a wooden dowel, and the nut is represented by a clothespin. Why did we choose to use a clothespin? Because there's a maximum force that this nut can support before it will fail. You can imagine that there's only so much weight that could be borne by this clothespin hanging onto the wooden dowel here. And notice the middle level is hanging onto the same threaded rod with its own own pair of clothespins or nuts in real life. And then here's the lower level, and it's hanging on to this same rod with its own pair of nuts or clothespins in this model. So there's one continuous threaded rod going all the way through. So it's basically like a 2 or 3 story tall threaded rod. And you can imagine what a hassle it would be if you were building this on the construction site. Here's what the construction crew on site decided to do instead. Instead of one big long threaded rod, here's a short threaded rod from the girder to the top floor. But then here's another short threaded rod from the top floor to the middle floor. Here's another short threaded rod from the middle floor to the bottom floor of the sky deck. And then the same thing on the other side. So whereas in this case, the top floor is holding its own weight, the middle floor is holding its own weight, the bottom floor is holding its own weight. But what's happening here, the bottom floor is grabbing onto this pair of rods with its clothespins. The middle floor is grabbing onto this middle pair of rods with its pair of nuts. So it's not only holding its own weight, this connection is holding not only this weight, it's also, if you think about it, holding this weight. And then let's look at this upper floor. This rod from the middle floor coming up and being held with a nut here, and it has this rod from the middle floor being held with a nut here. It's being suspended from the ceiling with this pair of short threaded rods. So this nut down here that's holding the top floor to the upper threaded rod is holding not only this weight, but it's also holding this weight and this weight. Now what do you do when you create a spectacular new space with an amazing skywalk feature? You have a big party with people dancing, and people are all over this, all levels of this bridge. Let's put some weight on the lower dance floor, or the lower level of the sky bridge. And this is as designed by the architect. And this is as built by the on-site crew. And then we'll put a little bit of weight on the middle deck here. So this is as designed by the architect, and this is as built on site. And then we'll put a little bit more weight. We'll put a little bit of weight, you know, some people, maybe some of them dancing on the upper level as built, upper level as designed, and then the upper level as built. Oh my goodness. So it actually didn't take very much to see that the as-built version of this failed. Where did it fail? Is where the upper level grabbed on to the uppermost short-threaded rod. To some degree, this is a good metaphor for what we do in physics. Take a kind of simple to analyze or simple to build model which expresses some key property of real life and puts it into a form that in this case is easy for us to build and see, but more often in physics we put things into a form that's easy for us to analyze with pencil and paper equations. Where this model failed is the clothespin that represents the nut that held the upper deck onto the threaded rod. My hands are going to mimic that nut, and my body will mimic the upper deck, and this rope will mimic the threaded rod. So let's see if I'm still able to climb a rope. To mimic the demonstration with the skywalk, I should let go with my feet and only hang on with my hands. This is, so my body represents the upper deck. Now how about the lower deck? The lower deck will be a friend who's going to grab onto the same rope. So in the way the architect designed the structure, I hang on to the rope up here with my hands, and my friend hangs onto the rope down here with her hands, and that's just fine. Her hands are holding her weight, my hands are holding my weight. Now let's think about the way that the skywalk was actually built on site, which was different from the architect's design. And the way to envision that is to picture here. I'll make it easier for you to picture. So again, you can see it takes a little bit of effort for me to hold my own weight. Now imagine that my friend, instead of grabbing the rope with her own hands, imagine she instead just hangs onto my feet. So you've got my hands holding me to the rope, and then instead of just holding my own weight, I'm holding both my weight and her weight, because instead of grabbing the rope herself, she's grabbing my feet. So now imagine the struggle. So you can see the clear failure point will be that my hands can't hold on, because it's hard enough for me to hold my own weight, but my hands would have to bear, in addition, not only my weight, but my friend's weight at that connection between, right, because my hands represent the nut that connects the upper skywalk deck to the threaded rod.
You saw from my hands on the rope, and you also saw from where the wooden dowel and PVC pipe structure failed, that the problem is that whereas here was the original design with a single threaded rod, that's kind of like a single rope, and I'm the top floor, I'm grabbing onto the rope here, and then my friend down below is the bottom floor, and she's grabbing onto the rope there, and everything is fine. I hold my weight, she holds her weight. But then the way it was actually built, here's like the rope going up to the ceiling, and then my friend, instead of grabbing onto the same rope, my friend decides effectively to grab onto my feet. And then this nut right here, which is the clothespin that failed in the first model, this sort of represents my hands trying to hold onto the rope. We'll learn a few weeks from now how to draw free body diagrams as a graphical method to analyze forces, and then later to analyze torques. But in any case, just the fact that the vocabulary word free body diagram appears in Henry Petrosky's book, I think tells you that the physics we'll study this semester has some connection to architecture. So he drew a force diagram to represent how big is the force between the top floor and the top threaded rod, which is communicated by this nut. And his claim is that force is twice as big in the as-built version as it was in the as-designed version. And you can see that the threaded rod, which is connecting the top floor to the ceiling, pulls out of the girder for the top floor. In the as-designed version, I'm up here, I hold the rope, my friend is down here, she holds the rope, my hands hold my weight, her hands hold her weight. And then here's the as-built method, where I'm up here, I'm holding the rope, and then my friend, instead of holding onto the rope herself, she holds onto my feet. And then you have to imagine, well, what happens here where my hands meet the rope? Like, are my hands holding just my weight, or are my hands holding my weight plus her weight? I'm Bill Ashmanskas. I'm the instructor for Physics for Architects. I've been teaching this course since 2011. The name Ashmanskas is a little bit tricky to pronounce. Even if you can pronounce it, it's a lot of syllables. Usually it's easier. I know that in architecture, you often call your studio instructors by their first names. So you can call me Bill. I'm perfectly fine with you calling me Bill. If you're not comfortable with that, you can call me Dr. Bill. Some people like to say Dr. Ashmanskas. You're welcome to say that. I just find it to be an awful lot of syllables. So I teach physics and I teach electronics here in the physics department. And I design electronics for research projects, both in the radiology department and in the physics department. So the design work that I do usually involves writing computer code, but sometimes I use CAD software for printed circuit board design. So to that degree, I can relate to all the time that you, if you're in the architecture program, spend using CAD software to make computer models of something that you intend to be realized in the real world. I grew up in the suburbs of Boston, where my dad built wood frame houses throughout my childhood. And I actually worked for him one summer. It was the summer before my senior year of high school. That taught me a lot about what holds our houses up. So it sort of felt like destiny that I should teach physics for architects someday, after in so much of my youth seeing blueprints for houses and seeing half-built houses, and even working on building a whole bunch of interior partitions and a few exterior walls for houses one summer with my dad. We're typically going to have a combination of reading textbook chapters and watching videos due on Mondays and Wednesdays. Doing that on your own time lets us spend most of our classroom time solving problems together in small groups. Stuff that's basically just information transfer, you'll do asynchronously, and then stuff that's really assimilating and using and truly learning the material we'll do together, and that way I'm nearby, the TA is nearby, and your classmates are nearby, so that when something doesn't make sense, you can discuss it right away. You're not stuck being frustrated for very long, and I think it should be a more engaging way to really practice the material as you learn it. Just as if you want to learn to play the piano, if you want to learn to be a better athlete, you want to say what kind of coach would you hire to help you to do that. You don't just watch videos of your coach playing the piano or exercising. You might watch somebody else do it at first to get the idea of what you have to learn, but then you only really learn it by doing it yourself. And so there's a difference between kind of the superficial knowledge that you can gain by watching somebody else do something or by reading about something versus the skill that you build up by doing it yourself. So the time that we spend together, that time is really, I intend for it to be spent on skill building, where you're really practicing and making the ideas really make sense in your own mind, and checking whether your own mind is really able to work out an answer. Let's just reflect a little bit on why we're here together. It may be that you're here just to take a college physics course for the sector requirement. So Physics 8 meets the physical world sector requirement. So that's terrific. So my terms are just that you put in a consistent 8 to 10 hours a week, each week total. That's the whole thing. That's coming to class, that's reading, watching videos, solving the problems, everything. And I try to keep it consistent week to week. And in return, I'll do my best to make the course fun, informative, and stress-free for you. Now, you may be here because some kind of a college physics course is required for entrance to most graduate programs in architecture. And if that's true for you, I think this course is an especially good fit because we really try to tailor its content to your needs. We try to tailor its delivery to your visual learning style. But I think more generally, you're here in this course if you're an architecture major or in a related field, because many of you someday are going to design things that are going to exist and they're going to be seen and they're going to function in the physical world that surrounds us. A better understanding of the physical world will make you a better designer of such things. Also, if you work with engineers on designs, then you may not be the person doing all of the detailed calculations. It may be that the engineer will do that for you, but you need to be able to ask good questions, and you will be able to ask better questions, I think, of the technical people on your team if you all speak the same language. And I think that a solid grounding in physics helps you to speak that same language. So this semester, we'll be focusing on mechanics, which should prepare you well for the structures course that many of you will take as seniors. So we'll be learning, or in many cases relearning, Newton's laws of motion, and you're going to exercise that mathematical side of your brain. And it may be, maybe you're a senior now, and the last time you took a math course was your freshman year. Often it's true that kind of mathematical side of your brain has had a couple of years to be a little bit less exercised. So it's good, actually. One thing that really makes learning stick is if you allow it to sit for a while without using it, and then you wake it up and use it again, especially if you use it again in a new context. So I think this is really going to wake up and exercise that mathematical side of your brain. So I think it'll be a fun way to really solidify that math knowledge that you have maybe from your freshman year of college. Professor Farley, who teaches structures, he tells me that he wants students to enter his course with a solid understanding of forces, torques, vectors, and trigonometry. So one key goal of Physics 8 is to leave you very well prepared for his course. And he always tells me that the students who have come through this course have entered his course extremely well prepared for the learning that they'll do in his course. So if you are in that program, I really think this course is excellent preparation. Two topics that appear in Mazur Chapter 1 that could be useful are estimation and unit conversion. Let's try to combine them both in this question. Let's estimate the mass of water in a rooftop swimming pool. You'll do another estimation on the first day of class. You will estimate the mass of the Great Pyramid of Giza. So I guess we can try to remember mass is volume times density. Then we want to know what's the volume of water in our rooftop swimming pool. And then we want to know what is the density of water. I'm going to combine these things together. Now, I didn't give you any details about our rooftop swimming pool. And that's on purpose. So often the idea behind an estimation problem in physics is you want to work out an approximate answer. And It doesn't have to be plus or minus 1%. Maybe plus or minus 25% is good enough. Maybe plus or minus a factor of 2 is good enough. So we want to estimate roughly an answer to a question which may not be perfectly posed, just to get a rough idea of what value would be plausible. So then we'd say, okay, what's consistent with our expectation versus what would be incredibly surprising? We really want to double check whether we understand what's happening. Let's just consider the volume of a rooftop swimming pool. So how big, I guess we want to know how long one lane is. Let's say we want it to be a pool you can swim laps in. The sheer pool on the UPenn campus at the Pot Truck Gym is 50 meters long, but usually there's a divider up so you can only swim in half of it. So let's say our rooftop swimming pool will be 25 meters long, because that's long enough comfortably to swim laps. I guess it could have been an Olympic-sized pool. We could have made it 50 meters long, but that'd be pretty extravagant for a rooftop pool. Or we could have made it maybe just 10 meters long, but then, if you're going to go to the trouble to make a pool, maybe you do want it to be long enough that people can use it for exercise lap swimming. So I think this is a plausible number for the length. Then you say, well, how wide is it? Actually, Professor Farley built himself a pool that is 1 lane wide so that he or his wife can swim laps back and forth. It's even a nice saltwater pool. But if you're going to put a pool on the roof of your high-rise building, it probably will want to accommodate more than one person swimming at a time. I'm going to say maybe it's 10 meters this way. Maybe it could be 5 meters. Could be 20 meters if it were like maybe designed for the swim team all going at once. But again, I think a kind of reasonable in between value is something like 10 meters wide. What is that? That's probably like 4 or 5 lanes. I mean, even 5 meters wide might be plausible, but let's say 10. And then another question is, how deep is it? You could have just 1 meter depth, and that's actually adequate. That's like the shallow end the whole way back and forth. The sheer pool on the Penn campus has a shallow end which is about 1 meter deep, and it has a deep end which is about 3 meters deep, and then the deep end sort of tapers. So you could pick a number of 1 meters or 2 meters. 3 meters would be the deep end the whole way. I would probably say 2 meters deep, but you could say 1 meter deep. That would be perfectly fine. I mean, just like this could have been 5 instead of 10. Maybe it could have been 20. I'm not sure it'd be 20, but it probably could be 5 or 10. Maybe this could have been 50 if you're being super extravagant. Maybe it could have been 10 if you're really trying to save space. So again, all of these inputs, maybe we could have made this one half as big, and maybe we could have made this one half as big or twice as big, and maybe we could have made this one half as big or twice as big. Although your estimate and my estimate probably won't be big all in the same direction or small all in the same direction. This is one interesting thing. You make an estimate and I make an estimate. We might choose different particular values, but you might choose one high and one low, and I might choose a different one high and a different one low, and it's likely that some of them will end up multiplying out to about the same volume. So this seems as if our volume is 25 meters times 10 meters times 2 meters, which is, let's see, 50 times 10, 500 cubic meters. Okay, and again, certainly we could have got a number that was 2 or 4 times bigger or 2 or 4 times smaller if we put in slightly different inputs, but it's a good ballpark number. What is the density of water? Well, you might remember that if you take a 1 cubic centimeter of water, it has a mass of 1 gram. So that's kind of a familiar number from school days. A familiar number for the density of water is 1 gram per cubic centimeter. So we'll use that number. But before we do that, let's just build a little bit more intuition. If we took, instead of 1 centimeter by 1 centimeter by 1 centimeter, suppose we took 10 centimeters by 10 centimeters by 10 centimeters. If I took a 10 centimeter by 10 centimeter by 10 centimeter cube of water, by the way, that's a liter. If you take a liter of water, what is the mass of a liter of water? If I told you it's a ton, you wouldn't believe me. And if I told you it's a gram, you wouldn't believe me. A liter of water turns out to have a mass of 1 kilogram. That sort of makes sense. When you have a 1 liter bottle of fizzy water or of soda, of milk, it makes sense. It weighs about a kilogram. So if we take 10 centimeters on a side, and we cube that, this is of water. And if we take 10 centimeters on a side and we cube that, that is 1 kilogram of water. Let's try to do it a little more systematically. If we take 10 centimeters cubed is the volume. As we said, mass is volume times density. If we take 10 centimeters cubed is the volume, and then times 1 gram per cubic centimeter is the density of water, then this is centimeters cubed upstairs, this is centimeters cubed downstairs, so we can cancel the centimeters cubed upstairs with the centimeters cubed downstairs. This is 10 to the 3 grams, so that's 10 to the 3rd power grams, which is 1,000 grams, which is 1 kilogram. Okay, so I guess maybe that's not too surprising. Then we could say the same thing with 1 meter by 1 meter by 1 meter and multiply it by this same familiar density of water, which was 1 gram per cubic centimeter. 1 meter cubed, and then we're going to multiply that by 1 gram per cubic centimeter. See, now the meter cubed doesn't cancel with the centimeters cubed. Uh-oh, what do I do? Well, 1 meter equals 100 centimeters. And so therefore, 1 meter divided by 100 centimeters equals 1. And you know that you can multiply by 1 without changing anything. So we're going to find some clever way to multiply by 1 such that the units that we don't want cancel out, and we're left only with the units that we do want. So let's multiply by 100 centimeters divided by 1 meter. 100 centimeters equals a meter. So 100 centimeters divided by 1 meter is just 1. We can multiply by 1. Doesn't change anything. That's not quite good enough because we have meters 3 times here, we have centimeters 3 times here. So we're going to cube this. Now that we've done that, now we have meters cubed upstairs, we have meters cubed downstairs. We can cancel that meter cubed with this meter cubed. And we have centimeters cubed upstairs, we have centimeters cubed downstairs. So we can cancel that centimeters cubed with that centimeters cubed. You have to be careful. This cube is still here multiplying the 100 So this is 1 gram times 100 cubed. What is 100 cubed? Well, you know, 100 is 10 to the 2 power. So 100 cubed is 10 to the 6th power. Right? 100 times 100 is 10,000 times 100 again is a million. So this is a million, or it's 10 to the 6th. So this is 10 to the 6th grams. And then, okay, maybe that's not too useful yet. So now we can multiply this by 1 again, because maybe we want to express it in kilograms. 1 kilogram is 1,000 grams. Okay, and 1,000 is the same as 10 to the 3, so maybe in this case it's more convenient to say 10 to the 3 grams. Then we can cancel grams downstairs with grams upstairs, and then 10 to the 6th divided by 10 to the 3. A million divided by 1,000 is 1,000, and you know that. So here's our 10 to the 3. What's left upstairs is 10 to the 3. So this is 10 to the 3 kilograms. That's 1,000 kilograms. That turns out to be 1 metric ton. The mass of a cube of water, which is 1 meter on each side, is 1 metric ton. Maybe that's not surprising. I mean, if you took that much water, it would weigh a ton, right? It seems like if we have 500 cubic meters of water here, we think we're heading for an answer of 500 tons. But let's be more careful. What did we do over here? We used our secondary school memory that density of water is 1 gram per cubic centimeter. And we said, okay, well, how about 10 centimeters on a side, all that cubed? And we said, okay, that's a kilogram of water. And how about 1 meter of water on a side as a cube? Well, that is a metric ton of water. Okay, let's go back to this statement here. So we say mass is volume times density. So we're going to say the mass of the swimming pool is 500 cubic meters. And then the density of water is 1 gram per cubic centimeter. But you say, well, I have a problem here because I have cubic meters upstairs and I have cubic centimeters downstairs, and I want things to cancel out and just leave me units of mass. So how am I going to make that happen? Let's find a way to multiply by 1. But let's say we want the mass in kilograms, so we can multiply by 1 kilogram per 1,000 grams. Okay, that'll get me kilograms upstairs. It still hasn't solved this problem. See, now I could say 1 meter divided by 100 centimeters, or I could do that multiple times. But this makes things even worse, because now I have even more meters upstairs and even more centimeters downstairs. So even though 1 meter divided by 100 centimeters equals 1, that's not the useful way to do this. I have to do it the other way, where I say I have 100 centimeters divided by 1 meter. That's a name for 1, so I can multiply by 1. 1 is the multiplicative identity. But I want to do this not once, I want to do this 3 times, so that now I get rid of the cubic meters upstairs and I get rid of the cubic centimeters downstairs. So this meter cube cancels with this meter cube, and this centimeter cube cancels with this centimeter cube. Then this gram cancels with this gram, and this is good. I have an answer in kilograms. Sometimes it's useful to use scientific notation, you know, you just use exponents. So we could say, well, 100 cubed is a million, and that's divided by 1,000, so that's 1,000, and this 500 is 500,000. Okay, we could do that. Or you could say, this is 500 times, this is kilograms, and this is 10 to the 3 downstairs. This is 10 to the 2 cubed, so 10 to the 2 cubed is 10 to the 6th. So this is 10 to the 6th. And now we have 10 to the 6 upstairs and 10 to the 3 downstairs. That leaves us with 10 to the 3. So that equals 500 times 10 to the 3 kilograms. That's fine, that's an acceptable answer. 500 times 10 to the 3 kilograms. You could also write this as 5 times 10 to the 5th kilograms. That's fine, because you could bring those zeros in there. Sometimes it's nice to have the exponent be a multiple of 3, because then you might say, well, kilograms, 10 to the 3 kilograms is like megagrams. Nobody says megagrams. Megagrams are actually metric tons. So another thing we could do if we wanted to is we could multiply by 1 metric ton is 1,000 kilograms. That's the name for 1. So then 10 to the 3 kilograms cancel with our 10 to the 3 kilograms, and the answer would be 500 tons. I like to spell ton. You know, I'm used to writing ton like this, T-O-N. But when I mean a metric ton, I write it the British way. I don't know if everybody does that, but I do it because it reminds me that I'm talking about metric tons. So using these dimensions for the pool, and again, assuming it's fresh water, I guess if it were salt water, it might be a few percent more dense, although at the level of our estimate, a few percent more dense isn't going to make any difference. A plausible value for the mass of the water in our rooftop swimming pool is like 500 tons. Now, an equally plausible number would be like 1,000 tons. Or 200 tons, maybe even 100 tons. So anyway, but probably bigger than 100 tons, and probably no more than 1,000 or 2,000 tons, because there's only so far we can stretch these factors. But anyway, my estimate for the mass of a rooftop swimming pool is 500 tons. So part of it is coming up with plausible input numbers, and part of it is remembering things like, okay, to get the mass, I have to know how big it is, and I have to know the density of water. And then part of it is then once you have numbers that have units, dimensions associated with them, the systematic way to put them together in a way that avoids mistakes is to use this cancellation and to keep multiplying by 1. You find ways to multiply by 1 until the units that you don't want disappear, and you're left with the units that you do want. So then you systematically go and cancel things from the numerator and denominator. And then another thing that you saw us do at the beginning is we said, well, before we put a whole bunch of numbers together, let's use our knowledge that the density of water is 1 gram per cubic centimeter, and then let's ask so the mass of 1 cubic centimeter of water is a gram, and say, okay, the mass of a cube of water, which is 10 centimeters on a side, that turns out to be a liter. The mass of a liter of water is a kilogram, and then the mass of a cube of water, which is 1 meter on a side, is a metric ton. So we said, okay, now we said a cubic meter of water has a mass of a metric ton, so if we can get a number for the volume in cubic meters, which you might have some intuition for, then we can directly connect that to metric tons. So that kind of gives us a check in case we messed up our multiplication application, that gives us kind of a reality check. It's often useful to approach something more than one way and remember your answer both ways and see if they agree with one another. So what you're going to do in class on the first day is you will say the Great Pyramid at Giza has a square base. And then you'll take the formula for the volume of a pyramid like that. I think it turns out to be 1/3 times the base times the height. And that gives you a volume, so you have some estimate for the base area and you have some estimate for the height. And then what's it built out of? It's some kind of stone, so then you have to say, well, I wonder what kind of stone it is, what's a plausible value for the density of stone. You'll come up with a number, and then you can look and see what the Wikipedia says, and you can see how close you came with your estimate.
Okay, so I will see you in class on Wednesday.